Hello everyone and welcome along to today's webinar. Thank you for joining us. Today's webinar is titled Can we calibrate in one fluid and operate in another? It's one of TÜVSÜD's webinars that are sponsored by the UK Government's Department for Science, Innovation and Technology, also known as DSIT. Just to let you know, this webinar is being recorded and it'll be available on our website in about approximately 1 week's time. In terms of today's webinar, we'd love to hear from you, so feel free to use the chat box if you have any questions throughout the webinar. At the end of today's webinar session, I'll have a Q&A and I'll answer some of the questions. Ideally, we'll get them all completed. If not, I'll follow up with the folk that have asked a question that hasn't been answered by email at a later date. So a good place to start is to introduce myself. So I'm Dr. Chris Mills. I'm a senior consultant here at TÜVSÜD in Glasgow. I've got an engineering doctorate from Coventry University and an honours degree from Strathclyde University in chemical and process engineering. I'm a chartered engineer. I've been with TÜVSÜD for approximately 16 years now, so quite a long time, working that period in flow measurement, mixture of consultancy and R&D. Do a lot of R&D, both government funded and also industry funded, and also consultancy type projects as well. I've got a lot of experience with flow measurement technologies, in particular Coriolis meters, ultrasonic, turbine, differential pressure, and PD meters, positive displacement devices. I work a lot on calibration methodologies, traceability chains, measurement uncertainty, and throughout my time here at TÜVSÜD, I've been involved in several new facilities, so the design, build, commissioning and operation of flow facilities. Also, I'm fortunate to represent NEL at a variety of different committees. So I represent NEL at the Euromet committee, also the Working Group for Fluid Flow, which is WGFF. I sit in various standard committees, so ISO and also Energy Institute HMC1. And I'm also the chairperson for the Measurement Focus Group, which are focus group meetings we have here in the UK. We have 2 in Aberdeen, 1 in Birmingham and 1 in London this year, so please go to our website if you want to find out more details. And I'm also the vice chairperson for the IMECO TC9, which is also known as FlowMeco. So as I say, today I'm going to be presenting on can we calibrate in one fluid and operate in another. Now, the purpose or the background to this presentation is that the question I'm often asked: can we calibrate in one fluid and operate in another? Now, I want to let you know at the very beginning, I'm not going to have all the definitive answers for you. This is more a topic that's of interest. I'm going to present some data and also just discuss some of the challenges and also where any TÜVSÜD/NEL are going in the future to help resolve and answer these questions, or this pertinent question. So the contents of today's presentation, we have the background, so a bit of background to the purpose of it. Small discussion of different meter types, then a bit about experiences we've had here at TÜVSÜD, and then recommendations and conclusions, and lastly a Q&A as well. So I also wanted to let you know, apologies for forgetting, today's webinar should take approximately 40 minutes, so we should be finished well within the hour, and that includes time for the Q&A as well. So thank you for taking the time for today's webinar. So the background. So obviously we have various different flow facilities here at TÜVSÜD in Glasgow, and I'm going to present some of them to you and go through them. I also, as I say, go to various conferences and technical forums, and I'm often asked, as I suspect a lot of other folk are asked at other laboratories that are performing research, can we calibrate in one fluid and operate in another? Now, it's a reasonable question, and I like to think I'm being extremely helpful when I answer maybe. It's and that's me not being obtuse. It's partly because there's so many variables. There's so many parameters that need to be known first to say whether you can calibrate in one fluid and operate in another. And in actual fact, if I was being semantic, I would say that if you ever send your flow meter to a calibration laboratory to be calibrated, then you're already calibrating in one fluid and then operating in another, because no two fluids are going to be identical, even if it's natural gas or if it's oil. Most flow facilities will utilise a different oil, potentially being just simply a mineral oil. The viscosity and density might be a close match, but they obviously won't be identical. And natural gas, the composition will vary. Or you might be sending it to a facility that calibrates with nitrogen, for example. So straight away, you could be already calibrating in one fluid and operating in another. However, I'm aware that's not really what folk are referring to. They're referring to newer, challenging applications. So applications with other fluids such as CO2. So one of the main challenges, the reason why we're asked it, is that there's a lack of flow facilities, or traceable flow facilities, shall I say, that offer these new challenging fluids. Obviously, they're not new fluids, but the applications are becoming more widespread, and there's definitely a requirement for things such as CO2 measurement. However, there's only a limited number of traceable flow laboratories globally that can offer calibrations with challenging fluids. For CO2, I recently published a journal paper looking at the flow measurement requirements for CO2, and there's a clear gap in the traceability chain, or the traceability flow facilities offerings for CO2, be it gas or liquid. There are now plans in place and some facilities, such as Tufsud, which I'll go into, that are offering gas CO2 calibrations. However, for liquid, it's even more challenging. There certainly is a lack of these facilities. Other fluid that is obviously very topical is hydrogen. And again, same as before, there's a limited number of flow facilities. There might be some that can offer gas flow, either in hydrogen flow for gas or liquid, but they're typically very, very small flow rates. There might be applications with hydrogen refueling stations, for example, very low flow, or domestic gas use trials, which we're also completing here at Tufsud for gas phase hydrogen. But what about larger industrial sized flow rates? There certainly is a lack of traceable flow facilities, although there's a lot of plans in place globally, but at present there's certainly a lack of these facilities. LNG. Now, LNG has been around for years. Typically, people were using volume measurements, so looking at the height of the fluid within a tank, using tank level gauges. However, there's now a push to use flow measurement techniques, so flow meters, and there's obviously a facility in the Netherlands from VSL that can calibrate meters for LNG use, which is excellent, but that's only one such facility. Now, it's great that it's there, but if we're to apply this all over the world, there's obviously going to be potentially a larger demand, and we're going to potentially need more facilities. Also, this VSL facility is looking to answer the question, does a water calibration transfer to LNG use? Now, again, there's multiple reasons why you want to know that, and it's not just for LNG, it's for hydrogen and CO2, because whilst there's a lack of traceable facilities for these challenging fluids, there's numerous facilities across the world that can offer calibrations with water that are fully traceable, have a low measurement uncertainty, and crucially, they're also relatively cheap as well. Now, if you can calibrate in water, then apply the meter with a known uncertainty that meets the required uncertainty targets, obviously, for hydrogen or for CO2 or for LNG, then that is the perfect scenario. However, we're currently in the situation just now where not enough research has been completed, or there's simply a lack of facilities to even validate as to whether a water calibration will transfer to CO2 or hydrogen, and LNG as well. It's almost like a chicken and egg situation we're in just now. We know what we want, and we're hoping a water calibration or an air/nitrogen calibration might transfer, but simply there's not enough data at present to say with any conviction whether it's the case or not. Ultimately, you want to see the data. Something that we have attempted to answer here at TÜV Süd, and there are other facilities around the world that offer high viscosity fluids. Now, at TÜV Süd, we can accommodate fluids up to 2000 centipoise, so extremely viscous, getting close to the viscosity of a syrup type, so fairly viscous. We can operate with Reynolds numbers all the way down to single digits through the laminar turbulent transitional flow regime and ascertain whether flow meters can be calibrated in water, then applied with these high viscosity fluids / low Reynolds number applications. And I'm going to show you some of the findings from that during today's presentation as well. So, as I say, there's a lack of traceable flow facilities. And I maybe might have said it in a joke, but unless you prove your flow meter on site in situ using a prover or a master meter, but the master meter might have been calibrated elsewhere, so there's a break in the chain there, you're potentially using a different fluid to the one you operate with. So the only way you're calibrating with the exact same fluid is if you're proving the meter on site. So anytime you send it to a calibration laboratory, you're using a different fluid. In NEL /TÜV Süd are using surrogate fluids in a lot of cases. We use nitrogen for gas, but we also now have carbon dioxide, and we also have a rig that can offer methane / natural gas and also hydrogen, or methane in place of natural gas. For our oils, we don't use crude oil, we use mineral oils. So again, we're using surrogate fluid, but we try to match other key parameters such as Reynolds number or fluid viscosity, for example, and maybe not quite the density. I'll show you some of the data to back that up. So if I was answering the person from before, we go back to his question, can we calibrate in one fluid and operate in another? Well, if I was attempting to be slightly more helpful this time when he says, can we calibrate in one fluid and operate in another? Rather than say maybe, it might be better to say yes. Some meters can be calibrated in one fluid and operated in another in service, but with a higher uncertainty than you would achieve if you calibrated with that specific fluid. So a bit more detail, but again, might not fully answer the question because there's not a simple answer to that question. So at NEL, we have various facilities that we have built over the last 30, 40 years. This is one of the newer facility that I was heavily involved in. I came up with the idea for this facility from noticing a gap. So about in 2014, we completed some trials, or 2013, completed some trials with a Coriolis meter, a couple of Coriolis meters in oil at elevated temperature and relatively low pressure. And we discovered that there was a slight temperature effect. And from that, we wondered if there was also a significant pressure effect that maybe wasn't fully documented or published by all the Coriolis manufacturers. So we completed a joint industry project, a JIP, with 14 sponsors, looking at 3 different Coriolis manufacturers of 2 meter sizes, so nominally 3-inch and 4-inch Coriolis meters from 3 of the main manufacturers. And we tested them at various pressures and also temperatures, and we discovered there was a clear temperature and pressure and also a viscosity / Reynolds number effect for Coriolis meters. However, there was a lack of traceable flow facilities that could operate at these elevated temperatures and pressures, certainly with a great deal of stability and a relatively low uncertainty. So as such, we designed a closed loop system that you can see on the screen. It utilises a Emerson compact prover. That's now the Brooks compact prover, 60 litre version, and 3 helical turbine devices. And then we have 2 test sections that you can see at the bottom of the screen. The facility operates from 20 to 80 degrees Celsius, from 4 bar to 100 bar gauge. We can keep temperature stability to nominally about 0.1 to 0.2 degrees C through a calibration, and the pressure to nominally 0.1 to 0.2 bar throughout the entire calibration. It's very good temperature and pressure stability. The flow range is normally 0.5 to 100 litres per second. And the measurement uncertainty for mass and volume is 0.08%. So relatively low uncertainty for such challenging conditions. So this facility has been used to conduct some of the research I'm going to show you in this presentation. I also have a single phase oil facility for low pressure. However, this can also accommodate both low viscosity and high viscosity fluids. The previous facility that I showed you, that elevated pressure and temperature one, only operates with a relatively low viscosity fluid in the region of 2 to 6 centipoise, depending upon the temperature and pressure that we're operating at. Whereas the oil flow facility can accommodate fluids up to 2000 centipoise, all the way down to nominally 1 centipoise. It has a gravimetric primary reference system, so a weigh tank, and it has PD secondary reference meters. It can operate in stop-start mode against the weigh tank or in recirculation mode via the PD meters. Pressure is relatively low, in the region of about 1 to 4 bar, and temperature range going from nominally 15 to 50 degrees Celsius, with a flow range of 0.05 to 200 litres a second. The uncertainty for a primary gravimetric system is 0.03% for mass and volume at K equals 2, and our secondary reference, so these positive displacement meters that are pre-calibrated against our weigh tank for temperature, pressure, flow rate and viscosity, they nominally have an uncertainty of 0.08% for fluids below 50 centipoise. For fluids greater than 50 centipoise, the uncertainty is 0.25%. We also have a gas flow loop with an external traceability chain. However, we're looking to bring that potentially in-house in the future. It can operate with one of 2 fluids. So historically it's operated with nitrogen. However, recently we've just completed the upgrade to offer CO2. So this facility can now operate with CO2. We have a combination of turbine and ultrasonic master meters, predominantly using ultrasonic master meters, but we also have turbine master meters that we can also use. The uncertainty of this facility is 0.35% for mass and volume at K equals 2. In terms of pressure, we can operate from 10 to 60 bar for nitrogen. For CO2 it's slightly less due to the phase envelope of CO2, so we operate from 10 to nominally 40-45 bar, because if you pressurize CO2 you start to go into the liquid phase. And the flow range is nominally 20 to 1600 meter cubed per hour. So this is one of our newer upgrades, as I say, to CO2, and it's now allowing us to conduct research as to whether a nitrogen calibration can transfer to a CO2 application. And we're looking at evaluating various different meter technologies. So we're going to have differential pressure, so orifice plates, venturi, cone meters, for example, and we're also going to look at ultrasonic, Coriolis, turbine and rotary type devices as well. So a lot of work planned with this facility now that we've upgraded it to CO2. So we're both doing R&D, but it's also commercially available as well for commercial calibrations. So what about liquid CO2? What else are we doing at present? Well, one of the key findings from my journal paper on the subject was that there's a lack of CO2 calibration facilities with primary standard traceability in the UK, but also globally. I think a lot of folk think maybe someone in America has an offering, or China, or Germany, Japan, they might think something has been completed in the UK, but in reality, there's a lack of liquid CO2 calibration facilities and gaseous ones as well with primary traceability. So what are we doing? Well, it's critical to establish these traceability chains. We really want to be able to calibrate meters if we're going to be widely implementing carbon capture, utilisation and storage. So if we're going to be utilising CCUS schemes, and we have the clusters here in the UK that are being implemented, we are moving forward rapidly with that, but at the very early level, we have to establish a traceability chain. So as the UK's Designated Institute for Flow Measurement, TÜV-SÜD, also known as NEL from the National Engineering Laboratory, we're moving to address this gap in two ways. Two fluids. So the gaseous CO2 flow loop that I've just mentioned, and that upgrade's been complete, and we're looking to bring full traceability in-house for that in future. And then to a liquid CO2 flow loop. So this is what I'm involved in just now. I'm working with the design of the liquid CO2 flow loop. We have some funding to build a relatively small scale, so nominal 2-inch facility with a primary, I should add, for liquid dense and supercritical CO2. So we're nominally aiming to operate up to 200 bar with CO2, and from very low temperatures, so potentially down to minus 50 degrees C up to nominally 50 degrees C. We're not going to operate this facility in the gaseous phase. This will only be in liquid dense / supercritical phases. We have a primary option currently being procured, and also secondary reference as well. And then we're designing the rest of the other parts of the rig, so the pumps and the heat exchangers, valving, etc. So this is ongoing just now. We are aiming to have this completed by the end of 2024 and undergoing commission and being commercially available in 2025. So it's a project we have funding for. It's currently in the design phase, and we're looking to complete the design and start procuring the rest of the equipment and building it at our facility here in Glasgow, Scotland. So that's a bit about the background. So as you can see, there certainly is a requirement for calibrating in one fluid and operating in another due to these lack of traceable flow facilities offering these challenging fluids. There's also folk that simply want to calibrate in water because it's cheap, readily available, and simply easier than calibrating in, say, gas or calibrating in a high viscosity fluid. So we can also understand those drivers as well. However, if we take it back to one of the first questions I will ask is, what is the meter type? What are you referring to? Because not all meters are applicable. So for example, we have turbine meters. Now, turbine meters for gas are different from turbine meters for liquids. And this is to a lot of folk, but not everyone's aware of this. So for example, if you have a turbine meter for gas use, you can't send it for calibration in water. It seems obvious, but it's something that we have to be aware of. Not all meters are suitable to be calibrated in a completely different fluid medium, and turbine meters are certainly one such device. PD meters are also similar. Again, if you have a gas PD meter, you can't calibrate it in liquid, and vice versa for both of them. So it's certainly challenging. PD meters in particular are viscosity sensitive devices, so you really do want to match fluid viscosity. Differential pressure meters. Now this is one such device that isn't so much fluid independent, but can be calibrated with one fluid, be it water or oil, and then used in gas, or calibrated in gas and then used with a liquid. So there certainly is various applications, and certainly we often calibrate flow meters for gaseous and water by matching number. Ultrasonic meters, again, similar to turbine devices and PD meters that I mentioned, they are fluid sensitive, and the design is sensitive to which fluid you're using. So a gas ultrasonic can't be applied to liquid use, and a liquid ultrasonic meter can't be used with gas. due to the different transducer frequencies in design. But then we come to perhaps the most common flow meter, which is, I'm just checking, can everyone still see the slides? I just want to know if you can maybe put a comment. Let me know if there's an issue, if the slides haven't appeared. I can try and refresh the screen. But just now, what I have on the slides just now is various different flow meter types. So let me try and see. I'm just going to click forward and see, hopefully it's working. Excellent. I think we can see it now. I think maybe there might have been a slight lag for some folk. We are aware that there are some audio issues at times. It appears to be the software that we're using. Apologies for that if it is interfering with today's webinar. So the main point from this slide is that only some meter types are truly fluid independent, such that they can be calibrated in one fluid, be it liquid, and then used in gas, or vice versa. Those two devices I have circled here, so that's differential pressure meters and Coriolis flow meters, and that's where we're focusing the vast majority of our research for this fluid transferability. And some of the results from today's presentation are going to be around Coriolis meters. So I'm just moving on to the next slide. Hopefully it's moving along for everyone else. And this is experience. So this is me going to start showing you some of our data here from NAL and what we're doing. So this slide here is the results for a Coriolis meter with respect to a low viscosity fluid similar to a kerosene. So it's a mineral oil with fluid properties very similar to kerosene. So density around about 800 kilogram per meter cubed, 750 to 800 kilogram per meter cubed, and viscosity in the range of 2 to 3 centistoke. We have 4 sets of data here. So you can see we have dark blue circles, which is kerosene at 10 degrees C, and we also have kerosene at 20, 30 and 40 degrees C. On the x-axis we have the reference flow rate, so that's our reference, obviously, whether it be the secondary reference in this case, which was a positive displacement meter pre-calibrated against a gravimetric system, or whether it was simply the gravimetric system and it was the mass with respect to the time given as our reference flow rate. On the y-axis we have the mass flow rate error, and that is the deviation between the device under test, in this case a Coriolis meter, with respect to our own reference system with a known uncertainty. I've also overlapped the meter specification, which is the blue line that you can see on the chart. You can see that for uncorrected low viscosity data, this is a brand new meter, pretty much out the box, just supplied to ourselves and tested. All the data is well within the manufacturer specification. The data looks good. Now what happens if we then apply that exact same meter in the same installation? In actual fact, the meter wasn't moved. We simply changed out the fluid from low viscosity to high viscosity. And you can see with the next set of data, and I've kept the same y-axis scale, so again from 0.5 to minus 1.5. This is with a fluid with the trade name Primol, but of more importance is the viscosity range, which is 50 to 300 centistoke depending on the temperature. And you can see here that near enough all the data is outside the manufacturer specification, apart from 2 rogue points down at nominally 10 kilograms a second with the 30 degree Primol data. That appears to be inside the meter, the manufacturer specification, but the rest isn't. Now I often get asked what's the issue here, and it's simply a known effect with Coriolis meters, certainly of certain geometry anyway, and that is a Reynolds number effect. So the meter's outside the specification, and you can see that there is certainly potentially a trend, but what if we plot that data with respect to Reynolds number? So now the same data as before. I have both the kerosene and that higher viscosity Primol data, plotting it all on the one chart, but this time with respect to pipe Reynolds number, as opposed to Coriolis tube temperature. This is the pipe, so nominal 6-inch device. And you can see that we're going from nominally about 200 or 300 Reynolds number all the way up into the near enough a million Reynolds number. You can see there's a clear Reynolds number dependence if you plot all the data together. However, the effect appears to be linear, and this is just one set of data for 1 metre I'm showing you, but we've had this facility operational now for well over a decade, I believe about 12 years or so. We have conducted a lot of research with a lot of Coriolis meters of different sizes, different manufacturers, and different fluid Reynolds numbers by changing the viscosity, changing the velocity, and the density. And we can categorically state that when we do witness Reynolds number effects, they do appear to be linear. So compensation certainly appears to be possible. We find that the Reynolds number effect is repeatable and reproducible, and such that if we change out fluid and then go back to that same Reynolds number, which you can see we've achieved here, we still get the same deviation, which is very good. So that's liquid. So for liquid use, for high viscosity fluids and for fluids that are viscosity critical, you can see that there is a potential to match Reynolds number. Now, to do that, you might need to simply use a medium fluid viscosity and a low viscosity to match the Reynolds number, or you might still need a very viscous fluid depending on your velocity, your pipe diameter, and your operating velocity. So something to be aware of, and I'll come back to the recommendations at the end. But the other question we often get asked is, what about gas meters? Can they be calibrated in water, and do you have a lot of data? Well, before we go into that, for Coriolis meters in particular, and it's true for other meters as well, but obviously for Coriolis meters being a mass device, what about the density and resulting mass flow differences? That's one of the real challenges. How do you match gas calibration with a liquid when the density is so different, and as such, the mass flow is also completely different? So to illustrate this, I have a meter manufacturer's flow rates from their datasheet for a liquid device. I've blocked out the model and name, obviously don't want to share that, but just to show you the nominal line size and the nominal flow rate. So you can see here we've got 2, 3 and 4 inch diameter meters, so DN 50, 80 and 100, and the nominal flow rate going for 2 inches about 48,000, and for 4 inch is nominally about 295,000 kilogram per hour for liquid. But what about gas? What do we do for gas? We can see here, again, I've taken out the model number, but these are 2, 3, 4 inch devices, and you can see that the gas flow rates are remarkably smaller. So 10,000 for the 2 inch up to about 62,000 for the 4 inch. And obviously don't expect you to remember it, but those gas flow rates are approximately 20% of the liquid mass flow. So what happens if we chart this? So on the next slide, I have a 3 inch Coriolis meter, and I have the nominal flow range for liquid and the nominal flow range for gas. So liquid in this case is the red and the gas is green. This is a meter specification, so I've got on the y-axis the percentage error, if you can imagine, for this device, and on the x-axis the reference mass flow in kilograms per hour. Now, the first obvious question is, if you're using it in gas, what range should you calibrate it for liquid? If you're using it gas, you're only using it in this very small range. Should you then calibrate in liquid flow in this very small range? Now that's a very small part of the turndown of a Coriolis meter, and if you are familiar with Coriolis meters, you'll be aware that at the lower end, and this is true for all meters, but for Coriolis meters you get zero effects. For other meters you start to get potentially velocity effects where it drops off. like a turbine meter, for example. But for the zero effects with Coriolis meters, they start to dominate. They start to have a larger relative effect. So it's an absolute number, the zero, but it has a larger relative effect on your performance. And as such, if you try and calibrate a gas meter and liquid at the same gas flow ranges, you're operating a very small part of the flow range, which is a real challenge. So you'll have potential zero effects to contend with, something you should be aware of. So before I go back to show you some gas data, I want to discuss zero effects. So what are they? And what effect can they have on the performance? Well, we complete a lot of R&D here at NAL, and one such program of work we looked at was a Coriolis meter with differing zero values. So Coriolis meter manufacturers often have a water calibration facility that's fully traceable. They all have a water calibration facility, and whether that's fully traceable or not. When the device is manufactured, they will calibrate it in their water facility and get their flow calibration factor. So, and when they do that, they'll also zero the device. So they'll have a factory zero. This should be published in your certificate you get when you purchase the device. And you can see here, I've manually inserted the factory zero back into this device rather than creating a new zero value when it's been installed. And you can see the results are slightly out of specification, suggesting that the factory zero is different from what the meter zero should be in service. Now this is as expected. I wouldn't recommend that you do this. So this is zero the manufacturer measured in their factory. It's not recommended for use. You should always check and verify your zero in situ, and if it needs to be re-zeroed, you follow the zero setting procedure from that manufacturer or NAL's procedure. I then followed the manufacturer zero procedure, and for this installation, it might not have been optimum installation, but you can see that some of the data was within specification. The zero was okay, maybe wasn't perfect. I just wanted to show you that even if you follow the manufacturer zero procedure, it doesn't mean you're always going to get a perfect zero. There could be other factors influencing the performance of that Coriolis meter. Now, why is this important? I'm trying to show you where the zero has an effect. You can see the meter manufacturer specification in red. You can see that some of the data points still sit outside when you do repeat points, and that's because the effect that zero can potentially have on your meter's performance. So this is critical if you're trying to use a gas meter and calibrate it in liquid where zero effects will potentially dominate. You will then apply that gas meter in use, having calibrated it at a very low mass flow rate for liquid, and the zero effects could potentially dominate, and you could be significantly out of specification and be operating with a very large uncertainty. So just to let you know, the zero measured using the manufacturer's zero procedure is the recommended process, even though we know there's a slight offset there, potentially, not a perfect zero. So what about gas meters calibrated in water? If we go back, I have two fluids here. I have water and I also have kerosene. So blue data points being water, and I've included the uncertainty bars because it's quite important to show you there's a different uncertainty between our facilities, and certainly for gas, where gas uncertainty becomes greater. So this is for liquid. Again, just to describe the chart, on the x-axis I've got reference mass flow in kilograms per hour, and on the y-axis I've got percentage error. You can see that both sets of data look okay. The kerosene slightly better than the water. However, please bear in mind this water facility actually has a higher uncertainty than kerosene. Both results are pretty close to the specification, certainly when you factor in the uncertainty bars. But what about gas? I've now included some data for this device that was kindly supplied to me for nitrogen and natural gas. So we have nitrogen here at NAL, we operated up to 30 bar, and we also have natural gas data that was supplied from an external laboratory for this device. Now there's various things to be aware of here. There's potential pressure effects for Coriolis meters, and there's also the effect of the flow range that you're operating across. Plus, also consider the increased uncertainty for gas. So the uncertainty for gas here, is in the region of 0.35, 0.25%, depending which facility was used. And you can see that if you actually look at the uncertainty bars, they are potentially within the gas specification, although those data points look as if they're slightly out. The point here is, what would you choose? How would you calibrate this device? Can you calibrate it in liquid? My recommendation, and it's not absolute, it certainly depends on your application, what your uncertainty is, what device you're using, the size of the device, and the availability of calibration fluids. One potential option is you do partly match mass flow. So for example, you pick 2 or 3 flow rates that match the same mass flow, and then you also match meter turndown. So you potentially match velocity, or you match the turndown of the liquid flow range with the turndown from the gas flow range. So say for example, in gas you're operating from 20 to 80% of the gas flow range. If you were calibrating in liquid, you would then try and match 20% to 80% of the liquid flow range, but also match at least 2 mass flow rates as well, just to give you an idea of what the range looks like. You'll find that Coriolis meters they're inherently linear devices. They should be extremely linear. So your liquid calibration should be linear, certainly at the higher range. The challenge is certainly down at the lower range, where these zero effects can certainly dominate. So that's gas, and I started to mention the slight effect there of pressure. So what about the pressure effect? So this again is a Coriolis meter, and you can see I'm showing a lot of data here, 10 separate calibrations. In this case I've named them as runs, from nominally 5 bar up to 80 bar, and I've also differed between whether I zeroed the device or didn't zero the device. The zero, in this case for this manufacturer, in this model type, the zero at pressure didn't appear to have an effect. So there wasn't a large effect with respect to the zero value that was recorded, whether we were at high or low pressure. Now, it's clear from these sets of results that there is a pressure effect. So on the y-axis we've got the deviation. You can see that with increasing pressure we appear to be getting an increased underread, so a decrease in the reported mass from the device. If I change the presentation of this set of data, which I'm going to do here, in this case it's the same set of data, even though it's all black data points, but on the x-axis now, rather than mass flow rate, I've changed it to pressure in bar. And you can see that it's a clear linear effect, which is very good. We want it to be linear. Linear ultimately means it's easily correctable. You can see we have the pressure effect there, that first term, so the gradient ultimately from the curve, or from the fit. Then we also have an offset, which is ultimately what the meter could have been adjusted by. So the meter was slightly out of specification by approximately 0.027%, and this could be adjusted. And then we have that zero effect, that pressure effect, which is minus 0.0076% per bar. So it's a linear effect. That's very good, but can it be extrapolated? We've only calibrated this up to 80 bar, but there's applications where people are using up to 200 bar potentially. Thankfully, this facility can operate up to 100 bar, so I derived this pressure correction with this set of data and then operated it at different pressures. So the next set of data I show you, I have 60 bar and 90 bar, which you can see we didn't calibrate the device at to derive the correction, but then calibrated it afterwards. We have the 60 bar data, which is purple, and the 90 bar data, which is green triangles. And if you look at the scale of the chart, typically Coriolis meters are 0.1% devices. Remember, the facility uncertainty is 0.08% as well. The vast majority of this data is well within 0.05%. So this shows that a traceable pressure correction can be extrapolated. So if you calibrate even up to say 40-50 bar and you get a nice linear pressure correction value, you can potentially then extrapolate that to 100 bar, 150 bar with confidence. So yes, it can. Yes, it can be extrapolated with a known uncertainty. The uncertainty will be slightly increased because it's outside of the range at which you derive the correction. So what are the recommendations and conclusions? So going back to the question, the title of today's webinar, can we calibrate in one fluid and operate in another? Well, the key finding is yes, some technologies, not all, can be calibrated in one fluid and used in another. However, you have to be mindful of the measurement uncertainty. It's also critical to bear in mind that water calibrations do not fully replicate surface conditions, so you will have an increased uncertainty. Things such as pressure, temperature, viscosity, Reynolds number effects are all potentially going to influence the performance and as such increase your measurement uncertainty. So one key question is, what is your target uncertainty? That's something that we always want to find out first before we make our recommendation. Pressure effects can be significant and require a traceable characterization. So Coriolis meters do have a pressure effect. It's known. Various manufacturers now publish their pressure effect. However, in a lot of cases, you still want to then derive your own traceable characterization for that individual device. We are finding from our research that the pressure effect doesn't appear to shift too much over time. I can't say this with certainty. If the device is very old, for example, and has been cycled through a lot of pressures, the pressure effect might change, so you might want to recharacterize it more often. But we're finding that it appears to be fairly stable, so you can maybe only require to calibrate it a couple of times just to check the stability of it. It's not something that has to be done continuously, potentially. So you don't need to do multiple pressures continuously. Some meters can be characterized against Reynolds number with viscous fluids, so Coriolis meters are one such device. Differential pressure meters can also be characterized with respect to Reynolds number by matching the Reynolds number as opposed to matching the fluid viscosity, which can be extremely challenging if it's elevated viscosity. You can instead match Reynolds number. But be mindful, you want to obviously be at a reasonable velocity. And for differential pressure meters, you obviously want to achieve a reasonable differential pressure. You can't simply operate at very low Reynolds numbers, but only be measuring, say, 5 or 10 millibar. That doesn't make sense. You're going to have a very large uncertainty. You would still need to be using, let's say, a medium viscosity fluid that gets you a reasonable differential pressure so that you're operating with a reasonable uncertainty. Coriolis meters in gaseous have a higher uncertainty than liquids. Again, some people aren't fully aware of that. They think Coriolis meters are just 0.1% devices for all fluids. They're nominally 0.1% for liquid, nominally about 0.3, 0.35% for gas, depending on manufacturer. But there are certain manufacturers that offer optimum devices with slightly lower uncertainties than those quoted, nominally 0.05% for liquid and about 0.25% for gas. Coriolis max flow in gas can be around 20% of the liquid flow due to the difference in the fluid density. So again, it's something to be mindful of when you're trying to calibrate it. What do you match? Do you match mass flow? Or do you match meter turn down? Or do you match velocity or Reynolds number? We do recommend trying to match that turn down, but also to at least try and replicate some of the mass flow as well. So match both mass flow for certain low flow rate points and then match meter turn down for the rest. And again, this isn't the optimum recommendation. The optimum recommendation is still to calibrate in the fluid or close to the same fluid. So gas for gas use, liquid for liquid use. But if you have a high uncertainty application and you're trying to use a relatively low cost calibration, there is the option of using a water calibration for gas use. Now, what about the challenging fluids? I realise I haven't presented the data so much on that apart from the high viscosity, and that's because we're still at the very early stages with it just now, even here at NAL, even though we're currently building and have built and commissioned some facilities. So we have that domestic gas hydrogen facility, we have the gas CO2 facility that was only just being commissioned, and we also have the liquid CO2 facility that we're building. I hope to then maybe have another webinar on a similar subject next year, and we'll certainly have more data to share with you at that point. We should be able to share with you some gas CO2 results and also potentially some gaseous hydrogen results. We might even have some preliminary results from our liquid CO2 rig as well. Hopefully you've found that useful. I realise I didn't answer all the the question for all fluids, but hopefully it's provided some guidance. Before I go, I want to also bring to your attention the conference that's been held in October this year. It's the Global Flow Measurement Workshop. I believe various folk that are currently on the webinar today have attended in the past. Some of you may not be aware of it, but it's one of the leading events in the flow community. It's going to be held in Aberdeen this year, and we have an abstract submission deadline that is quickly approaching. It's the 29th of February. So, however, if you maybe contact one of us at NAL, we could potentially extend that deadline if it's a bit short notice. If you're keen to present, please let us know by that 29th of February. If your abstract is going to be slightly delayed, we can hopefully get it included. Registration is open, so we have a super early bird with extra discount if you register before the 31st of March. Then we have the standard early bird, which with a slightly lower discount rate till the 31st of July, and then it moves to the standard delegate after that. So if you're keen to attend, please register, take advantage of the discount registration. And if you're keen to present, and I really recommend it, I've presented numerous times. I believe some people on the call today have presented in the past as well. It's a fantastic event to share your knowledge, your research, your experiences with your peers. And it's also just a great way of keeping up to date with what is going on in the measurement community. Historically, this event focused primarily on hydrocarbon oil and gas flow. That's still a large part of the conference. However, we're now looking at more emerging fluid applications. So hydrogen is covered, CO2, water flow is still covered. It's always an important topic around the world. So there's a whole host of things. We'll look at flare gas as well. So we'll look at emissions side of it. So I really do recommend that you visit our website, read a bit more, and potentially sign up. As I say, it's in Aberdeen this year, so transportation's readily available, easy to attend. So that's a bit about the conference. I'm going to go to the Q&A. I think we've got quite a lot of questions, so if you just bear with me, I'm going to have a read through and pick some of them. So some of the questions have been covered. So for example, I've been asked if the gas flow loop uses CO2 as a calibration fluid or nitrogen. So as covered in the presentation, we use both. So we can either operate in single phase nitrogen or we can operate in single phase CO2. And if you want more details, please get in touch. We can provide this specification. Another question we have here is about calibrating Coriolis meters at negative temperatures, so cold temperatures. For example, they said minus 40 degrees C. Now, I looked at elevated temperatures, so let's say ambient or normal temperature for the fluid is 20 degrees C. We operated up to say 80 degrees Celsius. We do not have a facility anyhow that can go to low temperatures. However, there is the LNG facility in VSL, and they have conducted some research as well. My experiences, taking it down to minus 40 degrees C, I would suspect, yes, there is a temperature effect. Temperature effect for Coriolis meters, I've operated them with correction and without correction, and we find it to be a linear effect. Going down to minus temperatures, I suspect it still is a linear effect that should be correctable by the manufacturer's patented corrections, but the uncertainty might be greater due to, again, a lack of traceable flow facilities. So I don't know if there's been enough research conducted outside of the VSL facility to say whether it's a linear correction that's fully compensated for by the meter. So it's one for VSL to potentially answer, or us with our new liquid CO2 facility that we're hopefully going to have this time next year. So someone's asked, are the results shared for a particular Coriolis meter manufacturer or design, or is it common for all Coriolis meters? Now this is, it's a good question. We are fortunate that we see the vast majority of Coriolis meter manufacturers here at TÜV Süd. So there's meters from, I won't name them, but everyone's aware of the main manufacturers, and they have slightly different designs. So you have ones with what's known as the U-tube, so a pronounced bend in the design, and we have ones with, say, a curved tube. We have ones that are straight tube, and these devices often operate, or they certainly do operate, at different oscillation frequencies. They have different size tubes, different tube materials, different wall thicknesses, and we find that all these parameters do affect the potential effects. So if we have Reynolds number effects, they do differ depending on the geometry and the oscillation frequency and the tube design. Pressure effects, again, that depends on the wall thickness with respect to the geometry as well. So a wall thickness, so a very thick walled tube for a small meter has a larger relative thickness than it would for a larger device. So as such, a larger device appears to be more affected by pressure than a smaller device. And again, there's reasons for that. So I would say that the only real way to know for a particular design and manufacturer is to calibrate at a traceable facility. But we find that the vast majority of choreometers do demonstrate a Reynolds number effect or a pressure effect, but it isn't true for all of them, and the magnitude at which they show that effect certainly differs as well. I realise it's now 3 o'clock, so I have other questions here. Apologies, I didn't manage to get to all of them, but I'm going to save them and I will get back to each person individually over the next couple of weeks. So I just want to take the time to thank you all again for attending today's webinar. I hope you found it useful.